How are quantum errors being reduced? Have you ever wondered how scientists and engineers tackle the tricky problem of errors in quantum computing? Let's break it down in a way that makes sense. Quantum errors are primarily reduced through a method called quantum error correction. This technique protects delicate quantum information by encoding it across multiple physical quantum bits, which we call qubits, to create a single logical qubit. When we talk about quantum error correction, we mean spreading quantum information in a way that if some physical qubits face errors, the overall logical qubit stays safe. To achieve this, we use error correction codes like surface codes, Bacon-Shear codes, and color codes. These codes determine how many physical qubits make up a logical qubit and how we can detect and fix errors. Recently, there have been exciting developments aimed at making these codes more efficient and scalable. For instance, new methods for error detection requiring fewer physical qubits for each logical qubit. This reduces the hardware needed and cuts costs. One innovative approach involves using specialized qubit designs, such as the dual-rail Diamond qubit, which helps suppress errors more effectively at the hardware level. This is a big step towards creating quantum computers that can handle errors better. Another important advancement is the use of artificial intelligence-based decoders. These decoders help speed up the process of identifying and correcting errors in real time as quantum systems grow larger. This capability is essential for making large-scale quantum computing practical. Additionally, new types of qubits, like qubits, actively work to stabilize against errors. They encode information in quantum states that are less vulnerable to certain types of errors. This approach reduces the complexity of the error correction process and significantly boosts the fidelity of logical qubits. With these advancements, error rates can drop to as low as 0.1% using fewer physical qubits. Experimental results from platforms like trapped ion quantum processors have shown remarkable improvements. In some cases, logical error rates have been reduced by factors ranging from 11 to 800 times compared to using physical qubits alone. These findings indicate a shift from noisy intermediate-scale quantum devices to more reliable, fault-tolerant quantum computers. In practical terms, reducing quantum errors allows quantum computers to perform complex tasks like simulations, optimization, and cryptography with greater reliability. Lower error rates mean that quantum algorithms can run longer and tackle more difficult problems, bringing quantum technology closer to real-world applications. To sum it up, quantum errors are being reduced through advanced error correction codes, innovative hardware designs, artificial intelligence-enhanced decoding, and novel qubit types. These combined efforts are paving the way for quantum computers that can operate effectively in practical scenarios.